So we're back live for the second half of today's lecture, and I should have remembered to do the screen share. Looks like it. In case I didn't remember, I'll do it now. Okay, so let's warm up by doing a little DFA programming, and we're going to do it by using the tool that you will be using for the second assignment, namely the Automata Tutor version 2.0. This is a tool that is being developed by people at the University of Pennsylvania, at the University of Illinois Urbana-Champaign in the United States. And these people deserve our biggest thanks for doing this job. They are not listening to me, so I can say that. And the fact that I know them doesn't mean that I'm biased. This is excellent stuff for you guys and for me. And gals, sorry. So I want to show you how to operate with this tool as we warm up for the second part for the lecture, okay? So here you have a practice problem that tells you to build a DFA that accepts all the strings of A's and B's that contain the pattern AB somewhere in them. Okay, so how do we do it? When you start the tool, you get your canvas like this, and you get a state with a self loop on A and B. If we really wanted to, we could mark this state as a final state. Would that be a good idea? No, it wouldn't be a good idea. Why? Because at the very least, we are going to accept what? Well, in this case, any number of A's and B's, but in particular, the empty string, which does not have AB in it. But there you are. I mean, the interesting thing here is to show you what kind of feedback you get when you make a mistake. So I made this mistake. It's not you. So you're not responsible for what happens. And anyway, I'm logged in as me, so these colleagues will figure out that I don't know what to do with DFAs. Well, actually, it's the tool who does that, and it doesn't care, really. So I think I need another state. Why? Because I want to figure out whether I've seen the pattern AB. So, well, actually, let's not make this final. So, if I see AB to begin with, it makes sense to loop because I haven't seen the pattern, the start of the pattern I'm looking for. But if I see an A, then I want to remember that I've seen an A. So I go to a new state, which is this state, where I remember that I've seen the first part of the pattern. And perhaps you can imagine that you want another state. And this one should really be final, that you reach when you've seen the second part of the pattern that you want to see. So if we see A, B, we are happy. So far, so good. Is this a correct DFA? You should accept all the strings that have AB somewhere in them. Okay, your colleagues are saying, some of them are saying no. What is wrong with it? Sorry? If B comes first, then we just loop until okay, so your colleague is saying, let's make another state and we make the B go there. And this goes to the final state when A comes. Let's try this. Why not? Well, I actually wanted to show you what kind of feedback you get. Oh no, I've reset the canvas, stupid. There you are. This is what happens when I get confused, which happens far too often. Okay, make final. B goes here. And then B goes here. A, okay, that's what was suggested. Okay, so let's see what grade we get. Okay, so if the solution is correct, the Automata Tutor answers correct more or less straight away. But it's thinking which means that the solution is not correct. But we get the 7 out of 10 from the automata tutor. And look at the feedback. It says, check the transitions out of state 0. The following counterexample might help. You accept B followed by A, which is not good. Okay? So let's remove state. Okay, so this state means I haven't seen anything of my pattern, the pattern AB yet. This state means I have seen the A in my pattern AB. This means I've seen AB. If you're in this state and you see another A, then you still have seen the A of the pattern AB. Yoo-hoo! You were right the first time. But I mean, this was not my aim. My aim was to show you the feedback that you get when you do it wrong. Sometimes the feedback will say, well, you have this accept state, which shouldn't be an accept state. So you fix it. And for each one of the assignments for assignment 2, you get 3 attempts at the correct solution. Every time you get feedback, and every time you get a grade, and the system will remember your highest score. This is like a game. Feedback is really good. Last year, I allowed unbounded, unlimited tries, and some people just never thought at all in between the tries. Since I want you to think, and it shouldn't take 144 tries to get an automaton right, well, I'm exaggerating slightly. Some people tried 65 times. Which is, for an automaton with 3 states, it seems like a bit of an overkill, isn't it? Yeah, so question. The problems are already there from 9 a.m. today. So you just sign in to the automaton. So the question was, when are the problems on the website? They are. So you will have to register for a course, which is this course. It has a special web page. You see, sort of, for now you are me. I'll show you what it looks like when you're me. There is a course called Discrete Mathematics, blah, 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 and I can manage the course. And there is an assignment here, which is already there. Okay? Fantastic. And on the assignment description, you also have the login information, everything you need. Okay, excellent. And then I can get all the grades for you at the press of a button. And you will use these also for the 3rd assignment. Unfortunately, we cannot use it for everything. That would be fantastic. But there you are. Life sucks sometimes. More often than sometimes, but that's another matter. Okay, so before we actually had our break, we saw that finite automata cannot accept a language like this. And this is summarized by a motto that goes under the name of finite automata can't count. Because if they could, then we could actually accept this language. They cannot remember how many zeros you've seen. Question? Zero problems open. So, okay, I need to create a new assignment. That's strange. Okay. Odd. Thank you very much for telling me. So I'll fix that afterwards. Because there should be 9 problems, actually, not 0. I'll create another problem set with the same name. So what was I saying? Yes, finite automata can't count. Sometimes people get carried away and they bring this conclusion to an extreme. Analogy is very powerful, but sometimes it can lead us astray. So one of the exercises for you, we are not going to do it now, you're going to do this at home at your leisure or during the exercise session. If somebody asks you to come up with a DFA that accepts the strings over the alphabet AB that have an equal number of occurrences of the pattern AB and of the pattern BA, your first reaction might be, finite automata can't count, so I can't do this. In reality, this time you can. Why? Because there is a lot of structure, a lot more structure to the type of solution that you can accept. So exercise, draw a DFA for this automata, that accepts this language. You can. So what languages can DFAs accept? We've seen examples of languages that DFA can accept. We've seen an example of a language that a DFA cannot accept. And in fact, I've told you that general reasons tell us that DFAs actually cannot accept most of the languages under the sky. Can we characterize precisely what languages DFA can accept? The answer is yes. They can accept precisely the regular languages. Now, what is so far for us the definition of a regular language? The definition that the textbook uses, which is not the standard definition, it's equivalent to it, is a language is regular if it can be generated by a regular grammar. And what is a regular grammar? Where there are many equivalent definitions, but I like to work with this definition here that says a grammar is regular if its productions are either of the form non-terminal goes to lambda or non-terminal goes to terminal followed by non-terminal. A language is regular if and only if it can be generated by a regular grammar. A regular grammar is one that has production only of these two forms. There are other equivalent definitions, so I would also accept those. It's just that this definition here allows us to draw the analogy between grammars, regular grammars, and DFAs very, very clearly. So what we are going to do now is to argue that every DFA accepts a regular language, a language for which you can construct a regular grammar. So how are we going to do this? We are going to do this the computer scientist way. And what is the computer scientist way? You give algorithms. You give a compiler that takes as input DFAs and spits out as target code grammars, regular grammars, and for each DFA that it takes as input, it spits out a regular grammar that generates the language that the DFA accepted. Okay? How does this work? So here's what I want to do. I want to construct a DFA to regular grammar converter. That's a compiler for you. It's a bit of a different compiler from the one that takes C++ programs as input, but there you are. It takes as input DFAs, and it spits out grammars. So that's a DFA. That's a grammar. But it doesn't spit out any odd grammar. The correctness criteria is that the language accepted by the input DFA is the same language that the grammar generates. So how are we going to do this? Let me show you how this works by example, and then you will see the general pattern at work. So let's take a concrete DFA, shall we? Let's take the DFA that accepts all strings of A's and B's that contain one A somewhere. Okay, should we accept the empty string? Does it contain an A somewhere? No. If we see an A, then we accept. And after we've seen 1A, it doesn't matter what follows. And here, if we are in the start state and we see a B, what do? We loop. This state means I haven't seen the thing I wanted to see. This means I've seen the A somewhere. Okay, so let me give these two states names. I'll call this capital S, and I'll call this A, capital A. So what is the idea? The idea is that these states are going to become non-terminals of my grammar. And what are the productions? What do you think? The productions could have two forms. Okay, so let me just write a different thing, not to confuse you here. The productions that I'm allowed to write, I have the form non-terminal goes to lambda, or non-terminal goes to symbol to terminal followed by non-terminal. Now, if you look at these type of productions, what do they look like? I'm in B. If I see a small c, I go to capital C. This looks like a transition, doesn't it, in the automaton? So why don't we turn every transition in the automaton into a production of my grammar? So I have a production that says, from AS, I go to BS. And another one that says, from S, I go to A, capital A. And how about this? This represents the loops that I have in my DFA. But I cannot stop here. Why? How many strings does this grammar generate? Remember, the role of a grammar is to generate strings of terminals. You want to get rid of the non-terminals at some point. Can you get rid of non-terminals here? No, you can't. There's something missing. Now, what is missing is some production that tells us that capital A is an accept state. That's when I want to terminate my derivation. And what is this production? A goes to lambda. That says, okay, since A is a state where the DFA would accept, here from A, I just remove the A. I finish the production of my string. And lo and behold, we have constructed a grammar that actually generates all of the strings that your input DFA accepts. That's an example, but it highlights the general pattern. What is the general pattern? The general pattern that this algorithm here, DFA to RG, uses is as follows. Give me a DFA. I will build a grammar whose non-terminals are all the states of your DFAs. What are the productions? All the transitions of the DFA. And moreover, for every final state, I will add a production from that final state, go to lambda. And what is the start symbol in the grammar? It will be the start state in the DFA. Okay, I encourage you to try this at home on several examples, but you will see that this actually works all the time. So what is it that you have constructed? You have constructed a compiler from DFAs to grammars, to regular grammars. So what does this mean? This means that everything that DFAs can accept, regular grammars can generate. So regular grammars are at least as powerful as DFAs. Are they more powerful? Actually, no. Everything that the regular grammar can do, a DFA can do. So we actually also have a compiler that goes the other way.
So you could just use a regular grammar when you don't use a DFA.
Absolutely. So your colleague is saying, then you can just use a regular grammar where you would normally use a DFA. Absolutely. The fact is that if you want to do pattern recognition, DFAs are much nicer. So in fact, there is an algorithm that also goes the other way around. You can build and you can devise an algorithm that turns a regular grammar into an equivalent DFAs. However, constructing this algorithm is much easier if you allow yourself to use something which is called non-deterministic finite automata. Why? Because grammars are inherently non-deterministic devices. For instance, suppose that you want to generate a grammar, you want to have a grammar, you want to construct a grammar that accepts all the strings of A's, A, B, and C's, in which every A is followed either by a B or by a C. Huh? So you want to generate all the strings in which every occurrence of A is followed by a B or a C. This sort of smells like it would be useful to have a device that allows us to non-deterministically choose between one of the possibilities, A followed by B or A followed by C. And you could do this just by looking at the A. Now, what is a non-deterministic finite automaton? Okay, a deterministic finite automaton is one where at each point, in each state, if you read your next input symbol, you will always be able to do so successfully, and there is exactly one state that you can reach by doing so. How about non-determinism? Well, first of all, when you have non-determinism, you can allow yourself the ability to crash as you compute. It's not true anymore that in every state where you are, you should be able to read and process any of the possible input symbols. For some of them, you may have no outgoing transition from your current state. In that case, pictorially, the computation crashes. You cannot read your next input symbol. Or, in your current state, you can read your next input symbol, but the machine can decide to go in one of possibly many different next states. The power of magic. Because you may ask, okay, well, this is really like life, if you wish. The only thing is that in life, we don't have the power of magic. We need to make choices. How do you know whether the choice you're making today is the right one to process your all inputs, the input string of your life correctly? You can't. But if you're using a DFA, you have access to an oracle. So every time if you're using an NFA, sorry, you have access to an oracle. So every time you read an input symbol A, you have 10 different possible states that you could reach. You ask your oracle. You don't want to make a mistake. You ask your oracle. You say, Oracle, which state should I go to? And the oracle will say, take the leftmost one, please. That's the only one that is going to lead you to success. Because the oracle is magic, has the power of magic. Or you have a magic wand, and the magic wand points you in the right direction. The key point, the mantra, at least informally, and then we will see it formally later on, the mantra is that such a non-deterministic device is going to accept an input string if it has some way of processing it correctly to completion, leading to an accept state. This machine, because of non-determinism, may have lots of different ways of processing the input string, but if there is one that can succeed, the machine will choose it using the power of magic. Okay, let's make this all very concrete. example. Let's assume that we want to develop a non-deterministic machine that accepts the language consisting of all the strings of A's and B's such that W ends with an A. And I allow you to use only 2 states, no more. 2 states. A DFA cannot do that. An NFA can, using the power of magic. Okay, I am in my start state. I read an input symbol. This could be an A or a B. First thing, is the start state an accept state? No, because the empty string does not end with an A. If the start state was an accept state, we would accept the empty string, and then we would be wrong. Okay, so let's assume that I see a B. Where do I go? I loop. Let's assume that I see an A. Where do I go? You go to a next state. I want you only to use 2 states, remember. The next state will be an accept state. Huh? And what now? Okay? Okay? But then you can go back and forth. Okay? So your colleague is saying this, if I understand correctly. Okay, so what do I do here? I loop if I see A. And if you see a B, you go back to the start state. Okay? This is a deterministic finite automaton that works. Now, what would be an equivalent? An equivalent NFA. An equivalent NFA, so this is a DFA. This is an NFA. That does this. Now, why does this work? Okay, remember, you have the power of magic, so you can guess when the symbol that you're reading is the last one. If it's the last one, it should be an A. And afterwards, you reach this state where you don't want to see anything else. Because if you see something else, you will not be able to process it. You don't have transitions coming out of this. The question is, how can you know that the A is the last symbol? Well, that's where you use the power of magic. Okay, so you ask your oracle. You say, Oracle, is my next symbol the last one? If the answer is yes, it's an A, you go to the final state. So why does this machine actually accept the language that we want? Because when you feed it with a string of the form W followed by A for some W, let me answer this question in a second. I repeat the question, and the machine has a way of processing it correctly. So that's the criterion for acceptance now. If the machine has a way of reading the whole input string and landing in an accept state, there could be lots of other ways of doing it wrong, but if the machine has a way of doing it right, it will accept the string. Okay, your colleague is saying, then he could try all the possibilities. That would be how you simulate an NFA. But it doesn't have to try because it has the power of magic. It has the oracle. It will zoom in to the right way of doing it if you can. And this brings me to the question that I didn't repeat before. Your colleague here is asking, what are the benefits of using NFAs? The benefits are, as we will see later on, is that they can be exponentially smaller than DFAs. There are languages that can be only recognized by exponentially big, in some sense, DFAs, but where you have linear size NFAs to accept them. So the benefit is size. And sometimes size matters. In this case, in reverse. Small is beautiful. Okay? So that's the idea. The idea is, every time you read an input symbol, you may have many different ways of processing that symbol, but if there is a way of doing it right, the machine will accept. So the machine will not accept an input string if it has no way of processing it right. And now you can imagine that the way of implementing this search would be to use massive parallelism and spawning off computations in parallel to try all of the possible executions of the NFA, or to do a brute force simulation of all of the possible executions of the NFA. So let's do an example. Of A last but one symbol is B. Okay, so these are all the strings of the form some string, B, and then some symbol. So if you read the string from the right, the second symbol that you read is a B. Yes? Okay, the question is, what are practical applications for NFAs? Well, NFAs are very easy to build to recognize patterns. They are easier to build than DFAs. So your compilers build NFAs to recognize the patterns, for instance, the collection of variable names. But we want to execute DFAs. So there is a tension there. So the DFAs are much more efficient to simulate than NFAs. But state, should it be an accept state? No, because sorry, my daughter was calling. I cannot take her call. So how do we go? How are we going to do this? Now you keep reading the input symbol. How are you going to know if you're reading the penultimate symbol in your string? You don't need to. You ask your oracle. You guess. Okay, so what do? I loop. On every symbol, I loop. This means this allows me to recognize or to read no matter what string comes before the last two symbols. Now, at a certain point, I see a symbol. If it's a B, I can say, okay, let me make a guess, an inspired guess. That's the penultimate one. It's the one but last. Okay, now I only want to see an A, and then the string should be finished. Or a B. I want to see one more symbol. Bingo. That's the NFA. Oh, the question is, do they not have error states? Well, you see, these are states where I don't accept. So you don't actually need all the error, so-called error states, because the non-deterministic finite automaton can crash on an input string. Oh, because the last symbol does not matter. The question is, why do you have A and B going to the accept state? Because the last symbol does not matter. It could be arbitrary. The only thing I want is that the one before it was a B. So, for instance, BA is a good string, but so is BB. ABA is a good string, but so is ABB. Now, it can be shown that no DFA with less than 4 states can actually recognize this language. If instead I wanted to recognize this language here, such that the third symbol from the right is B, it would be a piece of cake for you to build this automaton using the power of non-determinism. You just need to modify this automaton here. How would you modify it? Okay, you would need to add one more state. It would be this one. 4 states. No DFA with less than 8 states can do it. You can show it. If instead of third, you would write fourth symbol from the right should be a B, the nth position from the right, well, you could come up with an NFA with n+1 states to accept that, but no DFA with less than 2 to the n states would be able to recognize this language. Don't try it at home for large values of n, where large is even 5 or 6. You don't want to build by hand a DFA with 64 states. Or you can try if you really have nothing better to do with your lives. Okay, so this is by way of motivating the reason why we want to use the power of magic in our automata. On Thursday, we will see more formally what NFAs look like, how they differ from DFAs, and all that. Thank you. Yes.
You're asking me about course ID and course password.
Yes. Have you read this description of the assignment on my school?
Oh, this is in the assignment.
Yes.